Good afternoon to all of you. In this video, we wish to see the kinetic interpretation of internal energy and temperature. To start with, let us see what are the assumptions of the kinetic theory of gases. Number one, all gases consist of molecules moving randomly in all directions. This means that velocity takes continuous values and that too in different direction, different random directions. Then the size of the molecules are much smaller compared to the average distance between two molecules. Because the size of the molecule is treated as small, that is, it is treated as a particle, we ignore any rotation of the molecule about itself or any vibration within the molecule, that is neglected. And also, since the distances are large, the average distance between the two molecules is large, the molecules do not exert any electromagnetic force on one another. Remember, the molecules consist of charges, moving charges. So, electric field and magnetic field are produced. So, therefore, these electromagnetic forces don't exist and hence there is no potential energy involved. The only energy involved is the translational kinetic energy of the molecules. That is what comes out of this. The molecules undergo elastic collision with each other and the walls of the container. Because they undergo elastic collision, kinetic energy is conserved. Kinetic energy is not lost in any other way. It is not converted into, say, potential energy or excitation energy. All these are ignored and the kinetic energy is conserved. This is true if the walls and the gas, the walls of the container and the gas are at the same temperature. And we are assuming that the walls and the gas is at the same temperature. Then the molecules exert a force on each other and on the walls only during a collision. Otherwise, they do not exert any electromagnetic force on one another. Yes, this we have already seen. Only during a collision they exert a force, but otherwise they don't exert a force on each other. So therefore, again it follows. This point was discussed in point number 2, where we said the average distance between the two molecules was quite large. So again it follows from all this that the molecules, gas molecules, possess only translational kinetic energy and no other form of energy, either rotational, vibrational, or potential energy, electromagnetic potential energy. They do not possess these energies. Then the molecules obey Newton's law of motion. In calculating the pressure, we are going to use the Newton's second law. So that's why it is assumption. The time spent during a collision is negligibly small. Now, during the random motion of the molecules, there is going to be a lot of collisions. The collision time is negligibly small. That means we are saying most of the time the molecule is traveling. So all the time that we take in the travel time, the collision time is negligible and it can be is negligibly small and hence it can be neglected. So only time we consider is the travel time. Then when the gas is left for a sufficient time, it attains steady state. So let us see what the steady state means. The steady state has got two implications. One implication, which we have called as A, is that the number density of the molecules is independent of position, direction and time. Supposing at position 1, we consider a small volume delta V, and at that, in that delta V, let us say the number density is 5 into 10 power 18 molecules per meter cube at position 1. If you take position 2 and at same volume delta V, the number density will be the same. That is what we mean by saying that it is independent of position. It is also independent of direction. That is, whether you move towards the x direction, y direction or z direction, the number density will remain the same. Namely, for this example, if you have taken 5 into 10 power 18 molecules per meter cube. This number also does not change with time. Yes, for every instant it is the same. The second implication is that the distribution of molecules with different velocities is independent of position, direction and time. Supposing at position 1 we have a volume delta V, and in that delta V, let us say the distribution of molecules with different velocity is as given. We have just made a table as an example. Let's say 100 molecules have 600 meters per second speed in the x direction, 200 molecules have 700 meters per second in the x direction, 300 molecules 800 meters per second in the x direction, 200 900 meters per second in the x direction, 100 1000 meters per second in the x direction. This we have just taken as an example. Let's say this is the distribution of molecules with different velocities at position 1. Yes, and in the x direction. Now we are saying it is independent of direction. That means these very same velocities will be in the y direction also. These very same velocities will be in the z direction also. Yeah? So there is no preferential direction. All the three directions are equally preferred for the velocities. Then it is independent of position. At position 2 also, if we consider a small volume delta V, this would be the distribution of the molecules. This should be the distribution of molecules with different velocities. Yeah? And this doesn't change with time either. From instant to instant, it remains the same. Now, this assumption has simplified our calculation to a very great extent. Supposing we have a cube here of length L, of side L, cube of side L, yes, and supposing there is a molecule here which has just collided and it is having a velocity Vx1. That is, it would have velocity in the y direction and z direction also, but we are considering only the x direction. Let us say it has a velocity Vx1 and it is moving ahead. As it is moving ahead, it is going to have a collision. Now, during that collision, this velocity would change. Vx1 would change. But we said that the distribution of molecules with different velocities must not change. It does not change with time under steady state conditions. So therefore, in that same volume delta V, there must be another collision in which another molecule takes up this velocity Vx1. Now what we do is, we ignore both the collisions and say that this particular molecule proceeds with the same velocity Vx1 without any collision. Yes. So we are ignoring the collisions, and the time is also justified because we are saying that the time spent during a collision is negligibly small. So even that time for during the collision is small. So therefore our assumption is valid, and the particle therefore moves back and forth with the same velocity Vx1. That simplifies our calculations a lot. Now let us see how we can calculate the pressure exerted on the wall. For that, we shall see that for every collision on the wall, there is a change in momentum. Yeah. So this is the wall. On the wall, if it comes and strikes it at Vx1, because the collision is elastic, after the collision it will get back at mvx1. So the change in momentum is 2mvx1. This is the change in momentum, delta p. Yes, the change in momentum would be this minus this vectorially, so it would be 2m Vx1. Now the question is, how many collisions occur? Such collisions occur in 1 second. That is the frequency of collisions we would like to know. To do that, this molecule takes a time 2L by Vx1 to return to the wall. Yes, if it has started with Vx1 from this wall, it goes to the other wall and gets back. The time distance traveled is 2L. So 2L by Vx1 is the time it takes to get back to the wall. So the frequency, the number of times it will reach this wall in 1 second is 1 by t. So 1 by t is the frequency, which is Vx1 by 2L. Okay, that is the frequency. So this is in one collision. This is a change in momentum per collision. Change in momentum per collision. And there will be Vx1 by 2L, Vx1 by 2L collisions per second. So if you multiply these two, you will get the rate of change of momentum or the force. So change of momentum per collision is so much, and this is Vx1 by 2L. So 2 cancels here and you have m Vx1 squared by L. That would be the force that this particular molecule will exert on that wall. That wall is parallel to the YZ plane. Yes. Now, if there are n molecules, this would be a very large number. The force, total force, we can say the total force on it would be m Vx1 squared by L plus m Vx2 squared by L, so on up to Vxn squared by L. That would be the total force. Now, the velocity of a particular molecule would be in all the three directions. So we can say V1 squared is Vx1 squared plus Vy1 squared plus Vz1 squared. Yes. Similarly, we could write for V2 squared. V2 squared would be Vx2 squared plus Vy2 squared plus Vz2 squared. So on we could write. Now, if you add up all this, yes, what do we? You add that, you will have V1 squared plus V2 squared, so on up to Vn squared would be equal to, let us add all the x terms, Vx1 squared, Vx2 squared, so on. Then we would have the Vy1 terms, Vy terms, Vy1 squared, Vy2 squared, so on. And we would have the Z terms, Vz1 squared plus Vz2 squared, so on. Now we said that the distribution of molecules with different velocities is independent of direction. That means this y and this z would be the same as x because it is independent of direction. So therefore this we can say is 3 times Vx1 squared plus Vx2 squared, so on. Or we have this quantity as 1/3 of this. So coming to the force, the total force would be m by L is common, And here, instead of Vx squared, Vx1 squared plus Vx2 squared, we are going to put this quantity. V1 squared plus V2 squared plus Vn squared by 3. So this will be V1 squared plus V2 squared, so on up to Vn squared by 3. Now we define a statistical quantity known as the root mean square velocity of the molecules. That is called as VRMS. It is a statistical quantity. Why we say it is statistical is because the number of molecules are billions and billions, yes. So many of them. So it's not possible to really talk about the individual velocities and sum them up like that. So we are talking about a statistical quantity known as the root mean square velocity. This is nothing but square root of, take the square of all the molecules, velocities of all the molecules, take their mean, that is divided by n, and then take the root. Square them, take the mean and take the root. Go the reverse order. So that is VRMS. So therefore we can now say the total force is m by 3L into, this quantity can be written as n into VRMS square. Yes, that would be the total force. Now you can get the pressure. The pressure P is the force per unit area. The area is L squared. Yes. So this would be the total force by L squared. So this would be m by 3L into L squared into n into VRMS squared. M into n is the total mass of the gas and L cube is the volume of the gas. So therefore you get the pressure P as 1 by 3 rho VRMS square. So this is the result of the kinetic theory of gases. It's an important result. Yes, P equal to 1 by 3 rho VRMS squared. We shall see what this VRMS squared, the significance, physical significance of VRMS squared, we shall see in a short while. Now, we wish to see what is the internal energy of the gas. The internal energy of the gas is the sum total of the energies of all the molecules. Now, we said that the molecules possess only kinetic energy. So therefore the internal energy U would be half m V1 squared plus half m V2 squared, so on. So this would be half m into V1 squared plus V2 squared, so on up to Vn squared. This we can write it as half m into n, the total number of molecules, into VRMS squared. M into n gives the total mass of the gas, so that will be half m VRMS squared. That is the internal energy of the gas. Now, let us take a hypothetical situation. Supposing we have the same tube here of side L and the molecules are here with some velocities V1, V2, etc. There would be some distance between them, and let's say the distance of this is D1 from the wall, this is D2 and this is D3. Yes, there are several molecules with several distances. We have just shown two molecules and their distances from the wall. The side of the Q is L, so the volume is LQ. And let's say the pressure which this gas molecule exert on the wall is P. Let's say the pressure is P, given by this formula 1 by 3 rho Vrms squared. Yes, that is the pressure. Now, supposing we double all the distances without changing the velocities. So, what we are going to do is we are going to have double the size of the cube, and this V1, V2, etc. will be the same. V1 and V2 is going to be the same, except that this is 2L, 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 and this is 2D1, 2D2, and 2D3. So all the dimensions we have doubled, but the velocities we have not doubled. We have kept it as it is. Yes, so the molecules are there in the same place, except that they are farther apart. Yes, except that they are farther apart. So what can we say about the internal energy? The internal energy U will be the same, because it is given by half mv1 squared plus half m2 mv2 squared, etc. Since we are saying v1, v2, v3, etc. have not changed, the internal energy U would be the same. But let us see what has happened to the volume. The volume would have become 8 times. Yes, 2L the whole cube will be 8L cube. So the volume becomes 8 times. What happens to the pressure? Now see, if you consider a molecule moving from one wall to another, the velocity has not changed, but the distance has doubled. So the time it takes to return back to a wall will double, because the distance is doubled. So the frequency which is reciprocal of this will become half. So the frequency at which it hits this wall is going to be half. So the force will also become half, because the frequency is half. Now what has happened to the area of the wall? The area of the wall has become 4 times, because here it was L squared, now it is 2L into 2L, 4L squared. So the area has become 4 times. So what happens to the pressure? The pressure is forced by area, the pressure will become 1/8. Yes, pressure becomes 1/8. So the volume has become 8V and the pressure has become 1/8. You take the product of these two, the product has not changed, because earlier it was P into V, now it is P by 8 into 8V, which is again PV only. So this PV is a constant for this gas. Now we saw that U is also the same, it is a constant. Since U is constant and PV is also constant, we can expect that U will be a function of PV, of the product PV. Yes? So if you see this here, if you take this equation P equal to 1 by 3 rho Vrms squared. If you write rho as m by V into Vrms squared, you can write this as 3PV is equal to m Vrms squared, and if I divide by 2 on both sides, I can get 3 by 2 PV is equal to the internal energy U. So as we guessed, U is a function of P, product of P and V. Now we know, and V U is nothing but half m V Rms squared. Now we know PV is nRT from the ideal gas equation. So I can say U is 3 by 2 nRT, which is half m V Rms squared. Yes. So as per the kinetic theory, we find that the internal energy of a gas depends on the absolute temperature T. Yes, it is a function of the absolute temperature T. And the significance of Vrms squared is that it is proportional to T, or we can say T is proportional to Vrms squared, or we can say Vrms is proportional to square root of Kelvin temperature. So that is the significance of the statistical quantity Vrms squared. Now as you can see, if the temperature of the gas of a given gas increases, the internal energy will also increase. U is directly proportional to the temperature of the gas. If temperature triples, internal energy will also triple. Now, let us ask another question. Supposing we have a gas 1 here with internal energy U1, and let's say its temperature is T1. Let's say there is another gas here, gas 2, with internal energy U2 and the temperature is T2. Yes? The question we would like to ask is, if U2 is greater than U1, yes, is T2 greater than T1? This is the question we are asking. If the internal energy of this gas is more than the internal energy of this gas, can we say the temperature of this gas is more than the temperature of this gas? Because we are saying U is proportional to T. The answer is no. U is proportional to T for a given gas. Yeah? When you have two different gases, yes, let us try to understand why the temperatures need not be the same. As an example, let us consider a red hot pin. We have a red hot pin here and a bucket of water, let's say. There's a bucket of water. Okay? This pin is at, say, the red hot pin is obviously at a higher temperature than this. How do we say that? When you put this pin into this water, heat will flow from the pin to the water. The pin will cool down and the water will warm up. And both their temperatures will become equal. And then there will be no flow of heat from one to the other. So I can say that the temperature T2 of this pin is greater than the temperature T1 of this bucket of water. But because this bucket of water consists of a large number of, this pin I have drawn it too big, let's say it is a very small pin, yes, and this bucket is quite large, it's a huge bucket. So because of the sheer size, the internal energy, the sum total of the energy of all the molecules is going to be greater than the internal energy of this pin here. Yeah. So therefore, the internal energies are of U1 is greater than U2, but you find that the temperature T2 is greater than T1. So what is the measure of temperature then? Temperature is decided, or is a function, instead of saying decided, is a function of the average kinetic energy per molecule of a gas. So what we are basically saying is the average kinetic energy is U by N, which is nothing but we saw is 3 by 2 nRT, or half, let me write that expression, half m Vrms squared by N. Yes, this is the internal energy, average kinetic energy per molecule. So m by N would be half m Vrms squared. Yes. So it is this average kinetic energy that is a measure of the temperature. It is not the total internal energy. It is the average kinetic energy per molecule of a gas. So therefore, the spin has got a greater kinetic energy per molecule compared to the kinetic energy per molecule of this water. Here the average here is greater, the average here is less. So this is at a higher temperature, this is at a lower temperature. So temperature depends on the average kinetic energy of the gas molecule. So we can now see that if you have a mixture of gases, yes, if you have a gas at the same temperature T and there is gas 1 of mass m1 and there is gas 2 of having a molecular mass m2, and since they are at the same temperature, their average kinetic energies must be the same. So I can say half m1 Vrms 1 squared will be equal to half m2 into Vrms 2 squared. So if there are three gases, this will be half m3 Vrms 3 squared. So for a mixture of gases, okay, the average kinetic energy for a mixture of gases at the same temperature, the average kinetic energy per molecule happens to be the same. This is a constant. Yes. So if you write U as 3 by 2 nRT, U by N, we can write N as total number of molecules by the Avogadro number Na into R into T. So U by N would be 3 by 2 into R by Na into T. U by N is the average kinetic energy per molecule. Average kinetic energy per molecule. How much does that turn out to be? 3 by 2. R is the universal gas constant and Na is the Avogadro number, that is also a constant, universal constant. So R by Na is also a universal constant. It is called as the Boltzmann's constant. So we write it as kBT. So the average kinetic energy per molecule is given as 3 by 2 kBT by the kinetic theory of gases. As you can see here, the average kinetic energy does not depend on the mass of the molecule. The mass of the molecule is absent in this expression. Yes, it doesn't matter what the mass is. All that matters is the temperature. If the masses are different, the RMS velocities will be different. Yeah? But the kinetic energy is going to be the same, namely 3 by 2 kB